Welcome to the Q&A Ops channel. In this technical deep dive, we are exposing one of the most dangerous metrics in software engineering, the illusion of high code coverage. Line coverage only proves that the line of code was executed during a test. It does not guarantee that the underlying logic was actually asserted. To evaluate the true deterministic strengths of your test suite, you must implement mutation testing. Mutation testing operates by programmatically altering your source code at the abstract syntax tree or AST level. The engine injects deliberate algorithmic faults, known as mutants. It might change a greater than operator to less than, invert Boolean logic, or remove method calls entirely. It then runs your unit tests against this mutated bytecode. This architectural principle applies across your entire stack. Whether you are validating a Python microservice with mute, a compiled Go binary, or a high-performance Rust application using cargo-mutants, the goal is the same. If your test suite fails, the mutant is killed. If the tests pass despite the injected fault, the mutant survives, exposing a critical gap in your assertion density. Let's contextualize this within the classic test pyramid. Mutation testing does not constitute a new standalone tier. Instead, it acts as a meta-validation layer applied directly to the base of your pyramid. Because mutation engines require rapid, localized execution to process thousands of algorithmic permutations, they must be almost exclusively targeted at your unit and fast-running component tiers. Attempting to run mutation analysis against top-tier end-to-end UI tests is an architectural anti-pattern that will result in catastrophic pipeline timeouts and extreme flakiness. Therefore, mutation testing serves to harden your foundational code, proving the integrity of your lowest level assertions before you ever execute a single integration test. However, running a full mutation analysis requires executing your entire test suite hundreds or thousands of times. It is a massive computational burden. So, how do we strategically place this in the release cycle? First, engineers should execute targeted mutation tests locally on the exact modules they are refactoring. This creates a hyper-fast feedback loop, ensuring assertions are robust before a commit is even created. Next, to shift quality left without breaking the pipeline, you must implement incremental mutation testing on pre-merge in your PR. However, putting a full mutation analysis synchronously on every pull request will destroy developer velocity. By diffing the current commit against the target branch, the CI engine will only mutate the specific classes touched in the PR. This reduces compute time from hours to minutes. Finally, an exhaustive mutation analysis covering the entire codebase typically runs as an asynchronous nightly build, acting as a deep, comprehensive diagnostic scan before a release candidate is approved. To orchestrate this as a strict quality gate in your release pipeline, you cannot simply aim for a 100% mutation score. Instead, you enforce a strict degradation policy. In your Jenkins file or GitHub Actions YAML, you parse the mutation XML report. If an incoming pre-merge branch causes the overall mutation score to drop by even a fraction of a percent compared to the main branch, the pipeline triggers an immediate hard failure. This explicitly guarantees that net new code is rigorously tested with high-fidelity assertions. To summarize, stop trusting code coverage alone. Use mutation testing to validate your test suite across Python, Go, and Rust. Shift it left to the dev environment, use incremental scans pre-merge to protect developer velocity, and rely on post-merge nightly builds for full architectural validation. Thank you for watching. If you found this architectural breakdown valuable, please subscribe to the Q&A Ops channel and leave a like. See you in the next pipeline execution.